All right, this is 8.5. It is called counting principles. This will lead into probability. So the counting principle is basically starting to figure out what is my, like when you think of probability, it's the chances of doing this out of this. That's like the concept of probability, right? Today's focus is really how you find out of what. Like how many are the possibilities is kind of what the focus of the counting principle is. So we start with like our simple basic probability, which is, let's just say that there's 10 things in front of you and you want to know what the chances are of pulling from a specific color or number or whatever it is. That's your simple probability. And so the goal there is to put the number of what you're looking for over the total amount of items that are there. So let's say we said, what's the chances, or what's the probability of picking an even number between the numbers 1 and 10? So I'm going to figure out, like, obviously, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My total sample space, which is there's 10 items, right, would go in the bottom. And then the number of even numbers would go in the top. There are 1, 2, 3, 4, 5 even numbers. And then we always simplify it. So this would be a fraction that is 1/2. There will be questions we will do without a calculator, and they will stay as simplified fractions. There will be, or something like this could be rewritten as 0.5. And then there will be times in which you will use your calculator. Remember, this test will be split into 2 parts. There will be times in which you use your calculator, and those numbers could get a little bit more complicated. This obviously did not require a calculator. We wouldn't have needed it for it. All right, so example 1 just says, determine the number of ways a computer can randomly generate one or more such integers or pairs of integers from 1 to 15. So we're not looking for probability here. We're trying to figure out how many ways these things can be found. So if you're looking at the number of integers from 1 to 15. Okay, and your goal is to get an odd integer. So randomly generate from this set an odd integer. How many are there?
Here's what I found.
Oh, you're so helpful. How many odd integers fall from 1 to 15? 8, okay? Pay attention to the wording. From 1 through 15 obviously includes 1 and 15. If it said in between 1 and 15, we don't include 1 and 15. If it said from 1 to 15 inclusive, we include 1 to 15. So language is going to be super important in these word problems, okay? B says an integer that's divisible by 4. So as I look through these integers, which ones are divisible by 4? 4, 8, 12. How many are those? 3. Okay, so again, right now we're just figuring out, which is called the sample space. We're figuring out how many ways these things can be accomplished. Replacement and non-replacement is something you have to pay attention to. So if a random selection is given a fresh set each time, we consider this to be with replacement. So rolling a die, any of that would be with replacement, right? When you roll a die and let's say your goal is to get a 2, on the first round, that number does not disappear from your die, right? It's the same die every time. So rolling your die would be considered with replacement. Flipping a coin with replacement. Randomly generated number from a computer with replacement. Taking something out of a box but putting it back at the end with like physically with replacement, you're putting it back. If you have that selection removed after whatever that first round is, then we consider that to be without replacement. So there is a drawer of socks and you want to figure out how many red socks there are. If I take a sock out and keep it, the next time I go to pick, I have reduced my sample space. Okay, that would be without replacement. So example 2 says 8 pieces of paper are numbered from 1 to 8 and placed in a box. Once one piece of paper is drawn from the box, its number is written down and the piece of paper is returned to the box. Then a second piece of paper is drawn from the box and its number is written down. Finally, the 2 numbers are added together. In how many different ways can the sum of 12 be obtained? So the first thing you have to do is identify your replacement and non-replacement. So in this whole thing, what tells you that? What language tells you that? Return to the box. If it is returned to the box, then this is with replacement or without replacement? With replacement, which means we pull from the same set each time. So we're saying from the first time, they're 1, 2, 3, 4, 5, 6, 7, 8. Second time, it is also 1, 2, 3, 4, 5, 6, 7, 8. So how many combinations can I pull that make 12?
3.
What are they?
4, 8.
4 and 8.
6, 6.
5 and 7. 6 and 6. So that's 3 ways. What about the reverse, though? What if I pick first 6? Does it change my outcome? No, it's still 6 and 6. If I first pick 7, though, 7 can then get 5, and 8 can then get 4. So when it says you are picking a number and then picking another number, the order matters, because I can pick 4 first and 8 second, or I could pick 8 first and 4 second. So we count both. If you are reaching into the bag and you are pulling out 2 numbers at the same time, now that order does not matter. You're either going to get 4 and 8 or you're not. You can't get 4 and 8 and 8 and 4, if that makes sense, okay? So the question is, how many different ways can the sum of 12 be obtained? And we just said it is 1, 2, 1, 2, 3, 4, 5. If it asks for what they are, then it's 4 with, 4 with 8, 5 with 7, 6 with 6, 7 with 5, 8 with 4. Those are the 5 different ways that you can have a sum of 12. All right, very similar. It says 8 pieces of paper numbered from 1 to 8 and placed in a box. 1 piece of paper is drawn from the box. Its number is written down. The piece of paper is not returned to the box. Then a second piece of paper is drawn from the box and its number is written down. Same question. Finally, the 2 numbers are added together. How many different ways can the sum of 12 be obtained? What changed? Not replaced. Not returned to the box. How does that change my outcome from the last time?
You can't do a double 6.
I can't do 6 and 6. I can still do 4 and 8. I can still do 5 and 7. I can still do 8 and 4. I can still do 7 and 5. I cannot do 6 and 6. Because once I've taken the 6 out, it's gone. So there are 4 ways this time. Because it says you're not returning it to the box. So if you pull a 6 the first time, when you go back in to get a second number, the 6 is not there. All right, the fundamental counting principle helps us figure out the number of ways something can be done without physically going through all the options. So if E1 and E2 are 2 events, this could be pulling a number from the set the first time and then pulling a number from the set the second time. Those can be 2 different events. This can be flipping a coin and rolling a die. This can be pulling a rock out of a bag and then pulling a second rock out of a bag. Those are all considered to be events. The first event, E1, can occur M1 different ways. So you figure out how many different options there are for whatever you're trying to do the first time. And then after that's occurred, we say E2 can occur M2 different ways. So then we look at E2 and we say how many outcomes can that have? And the number of ways that 2 events can occur is M1 times M2. And that looks like this. How many different pairs of letters from the English alphabet are possible? How many letters are in the English alphabet? 20, good job. 26. So if I want a pair, then my 2 events are pulling a letter from the English alphabet the first time. So I want something in this spot that is from A to Z. Hey, holy moly. Right. A to Z. And then my second event is a second letter from A to Z. It says how many different pairs of letters, okay? So the first one is any of those 26 letters, right? So there we just said there's 26 letters here. Is A, B, and AA, are they different? That would be, those are different pairs, right? So the wording on here is tricky because it says different pairs. It doesn't mean that the letter can't repeat. It just means the pair itself cannot repeat, okay? So if there are 26 options in the first time, how many options are there the second time? 26 again. So if I want to know how many different, I literally multiply 26 times 26. Which is way faster than doing A with B, or A with A times, and then A with B, and then there's just 676. Like the long way around would literally, like you'd line up all your letters, and you'd have to count A with A with B, A with C, A with D, and so on and so forth. Then you'd go to B, B with A, like all of that, okay? So that is when we want to eliminate all that work. That would take you forever. So you multiply the numbers and the sets. All right, example 5 says a combination lock will open when the right choice of 3 numbers from 1 to 30 inclusive is selected. How many different lock combinations are possible? So 3 numbers, 1, 2, 3. Each of them has how many options? 30, because it is from 1 to 30 inclusive, which means you include 1 and you include 30. So there are 30 options for the first one. There are 30 options for the second one. There are 30 options for the third one. And then I just multiply them all out. There are 27,000 combination possibilities. Questions on that one? What if it had said from 0 to 30? Now how many are there? 31. Good. All right, example 6. In a certain state, each license plate number consists of 2 letters followed by a 4-digit number. How many distinct license plate numbers can be formed? So I do the same thing. Set up your digits / letters. There are 2 that are letters, A to Z and A to Z. And there are 4 that are a single digit number. So it says followed by a 4-digit number means there are 4 1-digit numbers. How many 1-digit numbers are there? 10. 0 counts. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 10 single-digit numbers. How many letters? Oh, wait, why did I do that? I put that in the wrong spot. This is the number. Number. How many letters did we say there are? 26. 26. No. 10. 10. 10. So we said 26 times 26 was 676. 1, 2, 3, 4 zeros. It has to be, right? There's a lot of cars on the road.
So are there repeated license plates?
No. Well, there's not that many. That's just in one state or one county or one license plate, right? Like you could have a Gator plate with the same thing as you have a Florida plate, or you could have those plates are different. But the state of Florida can't, yeah. Okay, permutation. So we're gonna talk about the difference between a permutation and a combination. And this is where I would say probability gets confusing. So you have to really understand the difference between those two. A permutation is determining the number of ways that n elements can be arranged in order. And what this means is that order is important. So if I take you guys and I line you up at the door and I say pick a seat and you get to choose from your seats, that first person, let's say that there's 17 of you, that first person, let's say there's 17 seats laid out. That first person has how many options to choose from? 17. Now I go to the second person and they get to choose a seat. How many do they have? 16. Then I go to the third person. 15. What's happening to our numbers? They're decreasing by 1. And then if I want to find the number of ways that this can be done, I multiply those numbers out. 17 times 16 times 15 times 14 times 13, all the way down. What is that called? A factorial. So permutations are done with factorials. That's what this little n factorial is, okay? So you have to pay attention to the wording of these things. If you are being arranged if you are being put in order, if something is being placed on a shelf, people are being arranged in a photo, you are finishing a race first, second, or third, like those kinds of, in a specific order, those are all considered to be permutations, okay? And so you figure out the number of people in that set, the number of items in that set. If I want to know how many ways I could rearrange the letters, okay, I would rearrange them in the number that there are there, factorial. So if it says how many ways can 10 objects be put in order, be arranged, be placed on a shelf, something like that, then it is 10 factorial, okay? Which you will use your calculator for the big ones. 10, oh my gosh. Oh, my brain's not working yet. 10, probability, exclamation mark, 3, 6, 2, 8, 8, 0, 0. 3,628,800 different ways to arrange 10 objects. It seems ridiculous, but if you think about it, you can literally, 1 and 2 can be there, 3, 4, 5, and then I can rearrange them, and I can rearrange them, and I can rearrange them, right?
Wait, how did you get that?
10 factorial. Sure, you're not. 7, example 7 says, find the number of permutations of the following letters. So again, you can say that this can be in order. I could rotate it forward and be B, C, D, E, F, A. Oh, F, A. I could rotate it again, C, D, E, F, A, B. Then I could switch them all individually. So this is a big number when you're talking about rearranging these things. But we're not going to spend our time trying to figure out all the possibilities, okay? We're going to use the factorial, which how many terms are there? 6 and 6 factorial. 720. It'll take you a long time to figure out all the different possibilities.
You think someone has somebody ever done that on the test?
I'm sure they, oh, I don't know, that high. Good? Okay. Now what happens if we only take a certain amount at a time? So let's say I line up 17 of you. Listen. Let's say I line up the 17 of you at the front of the class, but I only put out 3 seats. So 3 people can go at a time. To figure this out, we do something called PNR. So it's similar to CNR, but it's P for permutation. And the formula is this. N factorial over N minus R factorial, where R is the number of people you're taking at a time or the number of objects you're taking at a time. So N is the total amount in the set, which in that example would have been 17, right? And then if there are 3 chairs in front, I'm taking 3 of you at a time, then 3 is my R. So I do N factorial over N minus R factorial. On the calculator, this is in the same menu as CNR, which is under math probability. So example 8 says, find the number of permutations of 8 horses taken 3 at a time. So what is my N? 8. What is my R? 3. So I'm doing P8, 3, which is 8 factorial over 8 minus R factorial. And I get 8 factorial over 5 factorial. These are the ones, for some of them, we can do without the calculator because we can break it down. 8, 7, 6, 5 factorial over 5 factorial. And I have to do 8 times 7 times 6. I'm going to cheat, but you could have done that. That would be 56, or you could do left or right. 56 times 6, which is 336. Now try it with your calculator. So do the PNR using the probability menu on your calculator. Good. Good? Yes? Questions? All right. The last one is called distinguishable permutations. Nope, sorry, second to last thing because we're still going to talk about combinations. A distinguishable permutation. And let's say, and this says, suppose a set of n objects has n1 of one kind of object and n2 of a second kind of object and n3 of a third kind of object and so on. The number of distinguishable permutations of the n objects is given by n factorial over and 1 factorial and 2 factorial and 3 factorial. And what this means is for everything that has a repeated term. So let's just say, like, I'll go back to the Go Gators letters, right? If I look at the Go Gators letters, are there letters that repeat?
Yeah.
Yes. So if I grab the G, it has a repeated one. And if I grab the O, it repeats, right? So if I'm trying to arrange these, that messes up my combination because I could use this G or I could use this G and it gives you this same combination. So when you find this, you do the total set in the top. So I would still count how many. So if I use Go Gators as an example, because that just makes me happy. The total set is 1, 2, 3, 4, 5, 6, 7, 8. That's your N. So 8 factorial goes in the top. And then I could list out every distinct letter in that set or block or whatever we're using and say how many times it occurs factorial. So I could do this, don't do this, but I could do this. G, O, A, T, O. No, I already have O, sorry. R, S. And I could say G has 2 times, O has 2 times, A has 1 time, T has 1 time, R has 1 time, S has 1 time. And I could multiply all those factorials out. 2 in the denominator. 2 factorial, 2 factorial, 1 factorial, 1 factorial, 1 factorial, 1 factorial. But what is 1 factorial? Just 1. So I really don't need anything that's just there once. I only need to put in my denominator the ones that occur more than once. So this would be 8 factorial over 2 factorial times 2 factorial. Does that make sense? If I didn't have my calculator and I needed to break it down, I'd go to one of the 2 factorials, but there's still another one. I would cross these out. So these are gone. Like 2 goes into 4 twice, and I would multiply out all those numbers. If I do have my calculator, then I literally will write the fraction as it is. So 8 factorial, I'm going to put this in fraction form. 8 factorial over 2 factorial times 2 factorial, which is really just 2 times 2. Which is 10,080. This usually, you'll see these questions in words, like in the name blank, find the number of distinguishable permutations. So it's different because it's got a repeated factor. But you could do this with number blocks. You could do this with a lot of different things. But I would say most common you will see is words here, okay? But again, it is for something that has a set where something repeats and you want the distinguishable permutations.
Not for quite a while.
Hmm? It would have been, if you didn't use your calculator, it would have been 8 times 7 times 6 times 5 times 2 after we simplified it. All right, example 9. How many distinguishable ways can the letters banana be written? Try it. All right, so start with N. How many total letters are there? 6. So that's my numerator. Which letters repeat? A repeats and N repeats. How many times does A repeat? 3 times. So that's 3 factorial. And N repeats? 2 times. 2 factorial. So I'd get 6 times 5 times 4 times 3 factorial over 3 factorial. And then 2 times 1 if I didn't have the calculator. The 3's would cancel. 2 would go into 4 twice. And I'd get 30 times 2, which is 60. So that's manageable without a calculator. Just think that there will be times in which they're separated out and you'll have to. If there were a lot of letters, then you would have the calculator. Questions on that? So those are called distinguishable permutations. All right, then the last thing is combinations. And again, this is where probability gets confusing. Because the first thing you have to learn is it a permutation or is it a combination? And it is based on if the order matters. So a permutation, it does. Okay, if I put A and B or B and A, we count them both for a permutation because we're talking about where they're arranged and order matters. A combination is I'm just selecting letters out of a bin. What are the different ways that I can get letters? That is a combination. And this is when order does not matter. So this says, how many ways can numbers be taken? That's funny. Letters, that should say letters. Can letters be taken from the alphabet 3 at a time? And this is not saying in a specific order. So in this case, ABC is the same set as BCA, is the same set as CAB. If it said how many ways can they be arranged, now we're back to permutation. But this is CNR, and CNR should look familiar. It's the same exact thing as your binomial coefficient. CNR, which is how you find the number of ways a combination can happen, is n factorial over n minus r factorial times r factorial. So when we are talking about, because you're going to see a lot of different things, arranging people in a photo, that's a permutation. If you have a group of 10 people and you're saying, I want to just grab 3 people, and how many different ways can I grab those 3 people? Now it's a combination. If you're talking about finishing a race, or an Olympic, participating in the Olympics, something like that, and you're saying how many different ways can you finish first, second, or third, that's a permutation. But if you say how many different ways can they make it onto the podium, the order does not matter. Now it's a combination. If you're talking about running for office, okay, if you want to figure out how many different ways 10 people can fill the roles of president, vice president, secretary, whatever it is, that the order matters, permutation. But if you're talking about being selected to a board, now you're combination, because within that set, it doesn't matter what position you fill. So combination will always be a specific amount at a time. Combination's never the whole set. Like a whole set, how many ways can 10 items be arranged is always permutation, which is your factorial. Combination will always be a subset from a bigger group. So example 10 says, how many different ways can 3 letters be chosen from A, B, C, D, and E? So if they are being chosen and it says the order of the elements is not important, is that a combination or a permutation? This is a combination, so I'm going to do C and R.
So if it's not important, you just get rid of the R exclamation on the bottom?
No, if it is important, you get rid of it. If it's not important, the R is on the bottom. Yeah, because it should be a smaller number. Yep. All right. So what is my N? 5. And how many different ways can 3 letters be chosen? What is my R? 3. So this is 5 factorial over 5 minus 3 factorial times 3 factorial. This is 5 factorial over 2 factorial times 3 factorial. This would be 5 times 4 times 3 factorial over 3 factorial times 2 times 1. And the 3 factorials cancel, and the 2 goes into 4 twice, and this is 10. The number of combinations out of a set will always be smaller than the number of permutations of a set. All right, B, a standard poker hand consists of 5 cards dealt from a deck of 52. How many different hands are possible? So literally what's in your hand, you are not worried about which is card 1, which is card 2, which is card 3, right? Like if you literally picture playing cards, you can arrange them in any way. It doesn't matter what order they're in. So this is what? Combination or permutation? Combination. How many different poker hands are possible? What's my N? 52. What's my R? 5. This time we're going to do it on. Go to math, go to probability, grab your NCR, 52, 5. 2,598,960. If it had said 5 cards are being selected from, and it asked you in how many ways can those cards be put in order, now you're talking permutation. So when order matters, permutation. When it doesn't, combination. Questions? So you're paying attention to replacement and non-replacement, and you're paying attention to combination versus permutation.